So I already given some introduction about differential amplifiers when we tried the simulation of common mode and differential mode for the differential amplifier. So you will have a better understanding now. So what is the purpose of a differential amplifier? So unlike a normal amplifier, here we are going to use two single-ended transistors. So that we are going to give two different input signals for the two transistors, and finally the output is going to be the difference of the two inputs with the amplified version. So that any kind of noise or any other common input signals will be cancelled, and the output signal will be the amplified version of the differential signal. So the purpose of the differential amplifier, or if you see the applications, it is mainly used in uh, integrated circuit applications, and other gain control, volume control applications in different areas. Okay, so let us see the theory in detail. Differential amplifiers are also called as diff amp. It is the input stage to virtually all op amps. So mainly we are going to use it in op amp fabrications. It is probably the most widely used amplifier building block in analog integrated circuits. The performance of the differential pair depends critically on the matching between the two sides of the circuit. So since we are using two single-ended transistors, so the performance, it will depend mainly on the matching, how well the two transistors are matched in their characteristics. So differential circuits are much less sensitive to noise and interference than single-ended circuits. So why we use differential amplifiers compared to a normal amplifier is it is much less sensitive to noise and interference compared with the single-ended case. And it also enables to bias the amplifier and to couple amplifier stages together without the need for bypass and coupling capacitors. So when we use a normal single-ended transistor for going to the next stage, when we want to use more than one stage, we use generally some kind of coupling. Either we use coupling capacitors, RC coupling, transformer coupling. There are different coupling. Here, there is no need for bypass or coupling capacitors when you go for more than one stage. So advantages, they are suitable for IC fabrication because of the availability of large number of transistors in IC at a relatively low cost. So it is cost-wise, it's very economic and also good performance. So that's why we prefer differential amplifiers in IC fabrication. So this is a very basic block diagram for a differential amplifier. So we have two inputs, V1 and V2, and this is the output V0. So output V0 will be A into V0 is the gain of the amplifier into the difference of the two inputs, V1 and V2. So the ideal output voltage is V0 equal to the gain multiplied with the difference of the two input signals. So here we have two different modes. One is the differential mode and the common mode. So this differential mode VD, it is represented as difference of the two inputs, and common mode will be the average of the two input signals, V1 and V2. Okay. So these equations show if V1 equal to V2, the differential mode input signal is 0, and if the common mode input signal will be equal. So V1 equal to V2. So this you know already what will be the kind of input for the differential mode and the common mode. This is a very simple example here shown in terms of numbers. So V1 is plus 10 microvolt, V2 is minus 10 microvolt. What will be the kind of differential mode output and common mode output? So differential mode will be the difference of the two input signals, so which is around 20 microvolt. Common mode will be 0. So here both are plus and minus. So if you add, it will be 0. And similarly, so other example here, V1 is 110 microvolt, V2 is 90 microvolt. So here the difference signal is around 20 microvolt, and the common mode, if you take the average, it is 100. So similarly, one goal of the design of differential amplifiers is to minimize the effect of the common mode input signal. So here, when we are taking the common mode output, so the effect of noise, so or any other signal will be cancelled out. So we have to minimize the effect of the common mode input signal. So this is a very basic circuit diagram for the MOS differential pair. Okay. So here we have two different MOS transistors, Q1 and Q2, and this VG1 and VG2 are the two input voltages which is given to the gate terminal. So VG1 is given to the gate terminal of Q1, VG2 respectively to the gate terminal of Q2. And here both source of Q1 and Q2 are tied together. And this I is the constant current source at the source. And RD represents the drain resistance. So drain resistance, it is common to both transistors. Means it will be the same value. Since we are having matched characteristics for the both transistors, let us take the same value for the drain resistance for the both the transistors. VDD is the supply voltage, and ID1 and ID2 represents the drain current for the two transistors. VD1 and VD2 are the output voltage. So here we are going to take the output at the drain. So here this is a common source configuration. VD1 is the output voltage of the first transistor. VD2 represents the output voltage at the second transistor. So here the MOSFET should be operating in the saturation region. So it will work as an amplifier. It should not go into triode region or cutoff region.
VDD and
Yeah, VDD is the drain, supply voltage at the drain.
And VG1?
Yes.
VG1?
VG1 is the input voltage at the gate terminal of Q1. We're giving two different inputs for both transistors, Q1 and Q2. Gate input. Always we give input to the gate, no? For common source. So here instead of constant current source, we can either use a resistance or a constant current source which gives output resistance, high output resistance. Have you taken the circuit? So this circuit we are going to utilize for both the modes. That is for the differential mode operation as well as the common mode operation. In the differential mode operation, we are going to use VG1 different value and VG2 different value. Because in differential mode, both input voltages should be different. And in common mode, VG1 and VG2 are going to be equal. They are going to be same. So let us see, based on this input voltage, how the drain currents will differ. Based on this drain current, how the output voltage, VD1 and VD2 are going to be different. Okay. So based on that, the final output. So when we are taking the output, that is the difference of VD1 and VD2, how the output, final output will be changing based on this input voltage given at the gate in both the modes. Have you completed the circuit?
Yes, ma'am.
Okay. This is the general explanation given. The basic MOS differential pair configuration consists of two matched transistors, Q1 and Q2, whose sources are joined together, and it is biased by a constant current source I. So we have connected both source terminal together, and it is biased by a constant current source I. We assume that the current source is ideal and it has infinite output resistance. So this current source should have infinite output resistance. And whatever type of load is used, it is essential that MOSFET does not enter the triode region of operation. So we are going to consider the MOSFET operating in the saturation region. So now take this circuit diagram. This is for common mode. So previous circuit is the general circuit. Now we are going to use it in the common mode operation. So you mentioned this is the common mode voltage, common mode input signal, and you see here the gate terminal of Q2 is connected to the gate terminal of Q1. Okay, it is shorted. Draw this. So based on this, everything will change. So you can see there is a change in the drain current. Based on that, the output voltage equations are changing. Okay, so I will explain how it is. Take this circuit and mention the equation. So now you see here common mode input. Common mode input, it is going to be the same input given to both the transistors, MOS transistors. Now VGS is the gate to source voltage. So since we are giving common input for both the transistors, we are having the gate to source voltage is also common. It is same for both transistors. Otherwise, we will take this as VGS1 and VGS2. If the input voltage is different for both the transistors, we will take VGS1 and VGS2. So here it is same VGS, and the gate to source voltage for the Q2 is also same. Now VDD, this supply constant voltage, it is going to produce a bias current of capital I, right? DC current. So this current will be divided equally between the two transistors, two MOS transistors, as I by 2 and I by 2. Okay. And now, since this bias current also, it depends on the input supply. So here, this once this current, we are having I by 2 and I by 2, and what will be this voltage? VD1. So VD1, let us take VD1 as the output at the drain terminal of the Q1 transistor. Now VD1 will be the supply voltage VDD minus the drop across this resistance RD. What will be the voltage drop across this resistance RD? Current into resistance. That will be the voltage. So I by 2 is flowing here. So I by 2 into RD will give the drop. So VDD minus this drop, which is I by 2 into RD, will give the output voltage. That is VD1. Let us take it as VD1, which is at the Q1 transistor. So VD1 is VDD minus I by 2 RD. Similarly, at Q2, the output voltage VD2 is again VDT minus I by 2 RD. Since it is symmetric, both sides are symmetric. Since we are giving equal voltage, so the same current I by 2. So the drop is also same. So what will be the difference VD1 and VD2 here? VD1 minus VD2 will be yes, please. Are you following? What will be the difference between the voltages VD1 and VD2?
0.
0. 0. Yes, it will be 0. Okay. So theoretically, common mode output voltage will be 0. See, it will not respond. But practical scenario, we are getting some output. Did you observe in the simulation? We are getting some signal in microvolt range or nanovolt range, right? So the common mode, it will give you negative gain. Okay. So ideal case, it will be 0. Okay, the output voltage will be 0. It will not respond. And this Vs, it represents the source voltage. So this source voltage is calculated as this input voltage minus gate to source voltage, common mode input voltage minus gate to source voltage. And this is the equation for VGS. VGS can be represented in terms of threshold voltage VT plus the overdrive voltage. Or you have studied the equation for the overdrive voltage in terms of VGS and VT. Overdrive voltage is VGS minus VT. So this is rewritten as VGS equal to VT plus the overdrive voltage. And so we will see how we are getting this equation. Overdrive in terms of root of I by K dash W by L. Okay. So I think this equation also you have already studied. Overdrive voltage is represented in terms of root of I by K dash W by L. So we will see the equations, all these derivations in step by step. So in this circuit, they have mentioned all the equations here. I'm just explaining how we are getting these equations. In common mode, the two terminals are connected to the common input, the common mode voltage. So the gate voltages VG1 and VG2 equal to the gate inputs, it is equal to VCM. As Q1 and Q2 are matched, the biasing current I will divide equally between the transistors. So thus the drain current will be equal to I by 2. And the voltage at the sources will be Vs is represented as VCM minus VGS. And VGS is the gate to source voltage due to the current I by 2. Now, neglecting the channel length modulation. So we have, now we are going to write the current equation. So this current equation, generally we represent the current equation in terms of Kn dash W by L into VGS minus VT whole square, right? So here the current across the drain current, it is I by 2. So this is the equation for the drain current. So this drain current equal to I by 2 here. So we are substituting for I by 2 in terms of the drain current equal to half of Kn dash W by L VGS minus VT whole square. Now this VGS minus VT is equal to the overdrive voltage. So we can directly replace VGS minus VT as overdrive voltage. So now, so simplifying this equation, we are going to find overdrive voltage as root of I by Kn dash W by L. Okay. So the voltage is the drain, that is VD1 and VD2. So output voltage will be VDD minus I by 2 RD, because it is going to be the supply voltage minus the drop across the resistance RD. Hence the difference in the voltage at the drain will be 0, and vary the VCM as long as Q1 and Q2 are in the saturation. I will equally divide between them, and the voltage at the drain will not change. So finally the output will be nil. Okay. So now, so since you have mentioned all the equations in the circuit, if you want, you can take it. Otherwise, you can refer later these equations. If you want to take it, I have whatever I highlighted in red one. You want to take it, or it is already mentioned in the circuit. If you want, you can write only these equations I have highlighted in red for your reference. Okay. And this equation. Take this equation for VD1, VD2, and overdrive voltage. So we will refer these equations when doing the numericals. Please take the equations and have a better understanding, so that when we solve problems, it's very important to have a better understanding. Have you taken the equations? Yes.
No, ma'am, one minute.
Okay. Taken these two equations, the limiting condition, maximum and the minimum limits for the input voltage.
Ma'am would be there.
Yes. Okay, fine. So we will move to the differential mode input voltage. So here we are going to give VID. VID is the input voltage which is given to the gate of Q1 transistor, and Q2 transistor is simply grounded. Okay, for simplicity of the analysis, Q2 is simply grounded. It means we are giving zero input voltage for the Q2 transistor. So accordingly, you see here VGS1 and VGS2 are different. So previous case we have taken as VGS. So here it is VGS1 and VGS2. They are going to differ, and this ID1 and ID2 are going to be different based on the input voltage applied. Okay, and Vs is the voltage at the source. Okay, so you draw this circuit and mention the input voltage and the gate to source voltages. This is for the differential mode input.
Ma'am, what is the difference between this circuit and MOS differential pair?
Yeah, in the previous circuit you observe here, see VCM is the common mode input which is given to both the gate. It is
Ma'am,
the
more previous one. One
yeah,
more. The
previous
previous
first
circuit.
one. First circuit
Yes, ma'am.
is the general one. Yeah, you see here this is the general one. VG1 and VG2 are going to be the two different inputs. This is the general one. So in this general one, we have first tried the common mode input, which is the same input given to both. And the other one, the next one is the differential mode. Differential mode, we are giving different inputs. So it means VG1 equal to VID and VG2 equal to 0.
Okay.
According to your differential mode, according to your observation, VG1 will be equal to VID and VG2 is 0.
Okay, ma'am.
Okay. Since in differential mode we are just using this notation as VID. VID is the in order to represent as differential input. Accordingly, we have VGS1 and VGS2 representations. Okay. So now let us see here, based on this VID, how the drain currents are going to change, and based on that, how VD1 and VD2 are going to change. Have we taken this circuit?
Ma'am, 1 minute.
Yes. Okay. Now let us see the operation. In the figure, the gate of Q2 is grounded, that is VG2 is 0, and signal VID is applied at the gate of Q1. So VID will be here, VID is taken as the gate to source voltage 1 minus gate to source voltage 2. So this input voltage can be approximated as VGS1 minus VGS2, approximately VGS1 minus VGS2. And now let us see here what the scenario when VID will be positive. So when VID will be positive, this VGS1 will be greater than VGS2, and the current ID1 will be greater than ID2. So that is ID1 when VID will be high, ID1 will be high compared with ID2, right? And the differential output voltage. So what will happen to VD1 and VD2 when ID1 will be high? Now just keep in mind when ID1 is high. So let us say, so ID1 is nearly some 7 volt. ID2 is nearly 2 volt. So, or you can assume total bias current is I. ID1 is around 7 volt and 7 amps, and ID2 is 3 amps, right? So what will be the value of VD1? So what will be this RD into ID? What will be the drop here? So let us take the drain resistance as 10 kilo ohms, common value. Okay. So and VDD around 15 volt. You calculate VD1. Can one of you calculate? VDD is 15 volt, RD is 10 kilo ohms, and ID1, ID2 are 7 and 3 amps. What will be VD1 and VD2? VD1 will be VDD minus ID1 into RD. This supply minus the drop across this resistance will give the value of VD1. Calculate VD1 and VD2. So you take ID in milliamps. 7 milliamps and 3 milliamps.
Ma'am, can you note down the specifications?
Yeah, you note down VDD is 15 volt and RD you take. See, just for manipulation, I am telling RD you take some numerical value 10 kilo ohms. And ID1 and ID2 are 7 milliamps and 3 milliamps. Or even you take some minimal value for RD just for manipulation. You can even take 2 kilo ohms otherwise. 15 minus 2 into 7. So this is 1. VD1 is 1. And calculate
Yes,
VD2.
ma'am.
Yeah, calculate VD2.
Nine.
9, right? So VD2 is high, right? VD2 is high compared with VD1. So I mean to say here, when ID1 will be high, VD1 will be less. And when ID2 is less, VD2 will be high. So whenever the drain current passing is high, the drop across this resistance RD will be high. So that the voltage, the output final voltage at measured at the drain will be less. Okay, so whenever VID will be positive, or when the gate to source voltage of the first transistor is higher compared with the second transistor, so here the drain current will differ accordingly. Drain current will be ID1 will be higher compared with the drain current 2. So in such case, VD1 will be less compared with VD2. That's what is mentioned. VD2 minus VD1 will be positive. This is the scenario. Okay, so what will happen in the other scenario? The other scenario is when VID will be negative. So that is we are taking less value for VID, or we can say Q2 we are having high input voltage compared with the Q1 transistor. That in that time VGS2 will be dominating. So the reverse, everything will be reverse. VGS2 will be high compared with VGS1, and ID2 will be high compared with ID1, and VD1 minus VD2 will be positive. So that the drain current 2 will dominate compared with drain current 1. Okay, so this configuration responds to a differential input signal by giving a differential output signal between the drain. So we are going to have some differential signal VD2 minus VD1 for the first scenario. Okay, so you just write these equations. just for understanding. Okay. Yes. Have you taken?
Yes, ma'am.
Okay. Now, so by changing VID, we could arrive at a voltage that will steer all the bias current I into Q1. So the this bias current ID1 and ID2, it depends on the VID. So we can make all the bias current capital I, which can be made to, we can make it flow either across Q1 or Q2. Okay, it is controlled by VID. Okay, now we are going to at that point VGS1 will be such that the total drain current I will be equal to ID1. So let's say now we have changed VID in such a way that this ID1 is equal to the total current I. So in such case ID2 will be 0. There won't be any current flow across Q2 when ID1 will be equal to the total current I. So like this, we can make the total current I flow in either of the transistors. So similarly, when Q2 is conducting, Q1 will be off. So we can make the total current I flow across completely across ID2. It depends on the input voltage, VID. So VGS2 is reduced to a value equal to the threshold voltage VT. So at this point, when ID1 equal to I, VGS2, it is reduced to the threshold voltage so that this VS, this source voltage will be equal to minus VT. So now we are writing the drain current equation. So the drain current equation, let us now consider only Q1 transistor. Q2 is, ID2 is 0. So we are going to write the drain current equation as I because the total current is flowing across ID1. So this I equal to half of Kn dash W by L VGS minus VT. So here we are representing in terms of VGS1 since we are taking only Q1. VGS1 minus VT whole square. So from this, we are going to bring this expression for VGS1 in terms of VT plus root 2 times of I by Kn dash W by L. So this same expression, if you manipulate, you will get this VGS1 in terms of VGS1. So this root of I by Kn dash W by L, it is nothing but the overdrive voltage. So this is rewritten as root 2 times of VOV. VGS1 is VT plus root 2 times of VOV. And VOV is the overdrive voltage for a current of I by 2. For the full current I to be steered into Q1, so we have VID max and VID min. So we are going to calculate what is the maximum and the minimum limits for the input voltage. So that how we did for common mode, here also we are going to calculate what is VID max and VID min. So this VID max is given by VGS1 plus VS. So here we are substituting for VGS1, which is VT plus root 2 times VOV. VS, it is minus VT. So this plus VT and minus VT will cancel. Finally, we are going to have root 2 times VOV. So this is VID max. So VID max is root 2 times of the overdrive voltage. This is the final equation for VID max. Similarly, the reverse case, VID min will be minus root 2 times of overdrive voltage. So this will be the range for the max and the minimum limit for the input voltage. So you take this VID max equation. Okay. So the equation for VID min. So this, if VID is increased to root 2 times VOB, the current ID1 remains equal to I. So the total current will be equal to ID1. And VGS1 still remains equal to VT plus root 2 times VOB. And VS rises correspondingly, keeping Q2 off. So this is for the first case. Similarly, for the negative case, VID will be minus root 2 times VOB. This is the minimum value. Q1 will be off and Q2 will conduct all the current. So this is the total range. So we can write like this. VID is lying in the range minus root 2 VOV2 plus root 2 times of VOV. This is the total range. So you mentioned this range of VOV, VID.